In this video, we're going to look at returns, risk, and risk aversion. These are important concepts for understanding why different types of asset earn different levels of returns. You may think that these concepts are new. In fact, you deal with expected returns and risk and trade-offs between expected returns and risk every single day. People actually make decisions based on expected returns and risks in their everyday lives. For example, should you attend the investment management class today? The return, if you skip the class, would be an hour of leisure time, but the risk would be that you might miss an important topic for the exams. And you make a decision based on the expected return and the risk. Unfortunately, different people have different perceptions of expected returns and risk in our everyday activities. For example, which activity would you prefer? Shopping, golf, or skydiving? You can look at these activities and think about the expected returns that you would earn from engaging in these activities. You can also look at the risks. Now, many of you may think that skydiving is the riskiest option. But skydiving is probably safer than driving 20 miles to a shopping mall or a golf course. What's more, different people also have different risk tolerances. Some people are better able to cope with risk than others, and this will also affect their choices. In finance, to assess returns and risks, we use objective measures that can be calculated in spreadsheets. To calculate returns between time 0 and time 1, we're going to look at the following formula. Dividends that are paid on the stock between time 0 and time 1, plus the value of the stock at time 1 minus the value at time 0, all divided by the price at time 0. That's going to give us the return on the stock between time 0 and time 1. In finance, we have several measures of risk. For the time being, we're going to look at variance. And variance is just the average squared deviation of stock returns around the average return for that stock. We've introduced a few new concepts here. Average returns are often denoted R bar, and they're going to be calculated as the sum of all the returns divided by the number of returns we observe. If we think about stocks, we may pick Intel, and we may look at 5 years of monthly data for Intel. That would give us 60 months of return observations. Every month we'd have a new return for Intel. And we would calculate the sum of the returns over that 60-month period and then divide through by 60 to calculate the average return. The variance is just going to be the squared deviations, the average squared deviations around the average return, and the standard deviation is the square root of the variance. We will apply these concepts in Excel in a couple of minutes' time, but let's work through a simple example just to make sure we're all on the same page. Compute the standard deviation of the numbers 1, 2, 3, 4 and 5. The average value is 3. Now we've got to compute first of all the deviation from the average. In this case 1 minus 3. In this case it's 2 minus 3, 3 minus 3, 4 minus 3 and 5 minus 3. Next, we've got to compute the squared deviation. If we want to deal with variance, we need to calculate the squared deviation. The squared deviation in this case is going to be 4, 1, 0, 1, and 4. And the formula for variance says that you must sum up the squared deviations. If we add up the squared deviations, we're going to get a value of 10. The formula then tells us that we have to divide 10 by n minus 1, where n is the number of observations. We have 5 observations here, so we're going to divide through by 4, which gives us a variance of 2.5. The sample variance is 2.5, and the sample standard deviation is going to be equal to the square root of the variance, which is 1.58. Now let's have a look at this in Excel. Here we have price data for 5 stocks: Intel, AEP, Amazon, Merck and ExxonMobil. This data has all been downloaded from Yahoo Finance, and we downloaded the prices that have been adjusted to consider stock splits and dividend payments. When you're downloading data from Yahoo, you get to choose whether you want the raw price data or the adjusted price data, which includes dividends and stock splits. In this class, we're always going to want to download the adjusted price data. And we want to calculate returns for these 5 companies. So first of all, let's cut and paste the titles across. And we have 67 months of data. We need to find a quick way to calculate returns for all these companies. Well, if we want to calculate the return between month 1 and month 2 for Intel, we're going to follow our formula, which is going to be equal to the price at month 2 minus the price at month 1, all divided by the price at month 1, which gives us a return of minus 18.47%. We can do the same calculation for AEP, Amazon, Merck and ExxonMobil. The quick way to do this is to move the cursor to the bottom right hand corner of the cell, and you'll see it comes up as a plus sign. Just select and drag the cursor across all the way to ExxonMobil, then release the cursor, the left button that is, and you've now calculated returns for all 5 stocks. We'll do the same trick to calculate returns over time. We've now calculated returns for 66 months for Intel, AEP, Amazon, Merck and ExxonMobil. Very easy to do in a spreadsheet. Now let's calculate average returns, variance and standard deviation for these 5 stocks. Average returns, we're going to use the formula average, and the average is going to be for Intel, it's going to be H69 to H4. That's all the returns we have for Intel. So the average return for Intel is very, very small, 0.06% per month over this period. The variance is going to be equal to the formula VAR, brackets, and then let's select Intel's returns again. The variance is 0.011346, and the standard deviation, we can use the formula stdev, and again just select the returns for Intel, and we have now calculated average returns, variance and standard deviation. You can check the standard deviation calculation. How? Well, we know that standard deviation is the square root of the variance, and we could test that. So equals square root, which is SQRT, open brackets, and let's select the variance, close brackets, hit enter, and we see that the number is exactly the same as the number that we calculated using standard dev. To calculate the average returns, variance and standard deviation for all 5 stocks, let's select the three cells where we've calculated the average returns, variance and standard deviation for Intel. Go to the bottom right hand corner of these cells. So you get the plus sign. Press the left cursor key down and hold. Copy across to ExxonMobil and then take your finger off the left cursor key. We've now calculated average returns and risk for these 5 stocks. You can now see the power of Excel. We can very quickly do lots of calculations that would otherwise take a long time. Let's go back to our PowerPoint presentation. In our examples earlier, we saw that different people are likely to make different choices between shopping, golf and skydiving, and that they probably calculate different expected returns and different levels of risk. Even when everyone knows and agrees upon the expected returns and risk, people still make different choices. Why? Different people have different preferences for risk or different tolerances for risk. Some people are able to cope with taking high risks, while other people are very risk averse and don't like to take any risks if possible. We can measure people's risk aversion very quickly. Consider the following gamble. We're going to flip a coin. If it lands on heads, you win $10,000. But if it lands on tails, you have to pay $10,000. Would you take this gamble or not? Most people would probably say no to this gamble. It's a fair game. By that I mean that there's a 50% chance you're going to win $10,000 and a 50% chance you're going to lose $10,000. What is your expected return or your expected outcome? So the expected result is going to be equal to a 50% chance that you win 10,000 plus a 50% chance that you lose 10,000. So the expected return on this gamble is 0. It's a fair game. Most people will reject this gamble. But how big a win would you require from heads in order to take the gamble? Do you require $11,000, $15,000, $20,000? Maybe you require $40,000. Or if you're really risk averse, maybe you require $80,000 or even more from heads. If you took the original gamble, we would say that you are risk neutral. If you required a payoff of less than $10,000, you're risk loving. But if, as most people do, you required a payoff of more than $10,000, you're risk averse. And the larger the payoff you required, the more risk averse you are. What we'll see in class is that while for small gambles some people may be even risk loving, for large gambles with say $10,000 or $100,000, the vast majority of people are risk averse. It's useful to know that different people have different levels of risk aversion. Suppose you're a financial manager managing lots of different people's money. You know they have different levels of risk aversion, and so they're likely to want to invest in different products. The problem is, how do you know exactly what each person is going to want to invest in unless you talk to them all the time and ask them about every single option possible? You can't do that in reality. It's going to take up hours of your time and your customers' time. We want to know whether there's a mathematical way to characterize different people's preferences using some simple mathematical formula. Fortunately, economists came up with a measure called utility. And utility is a measure of satisfaction or desirability of a particular choice. Even better, economists formulated utility functions. These are functions that can represent a person's preferences. In this class, we're going to consider one type of utility function. The utility from investment X is equal to the expected returns on investment X minus lambda times by the variance of investment X. Lambda is a measure of the investor's risk aversion. You can see from this formula that utility goes up with expected returns, but utility is likely to go down with risk. So the more risk you take, the lower your utility, assuming that lambda is positive. Is lambda going to be positive? Well, lambda, for anyone who's risk averse, will always be positive. And the more risk averse you are, the larger the value of lambda. That makes sense because that means you attach a bigger penalty to risk. If you have a lambda of 0.5, the penalty for risk is not too much, but if you have a lambda of 10, the penalty is much greater. So this makes sense. If you're more risk averse, taking more risks really does reduce your utility. If you're risk neutral, in other words, you don't care about risk, then lambda will be equal to 0. All you care about is expected returns. If lambda is less than 0, you're risk loving. In fact, you get pleasure from taking risks. So this term is negative, but we're subtracting a negative number, which means we add. So utility actually increases from taking risks if you are risk loving. Now let's consider the real world. Here are two investments. I've plotted the returns from investing in the stock market and from investing in T-bills. These are short-term government bonds. You can see that the returns from investing in the stock market are very volatile. Lots of risk. Intuitively, we can see that the squared deviation from the mean from investing in the stock market is going to be high. Variance is going to be much higher from investing in the stock market relative to investing in government treasury bills. If individuals are risk averse, we would expect that the stock market will have to have higher average returns to compensate investors for bearing this extra risk. Is that true? In fact, that is true. The risk premium from investing in the stock market is almost 8% per year over the last 80 years. And this is the premium necessary to compensate investors for bearing stock market risk. On the graph, I've plotted the value of $1 invested in 1927. And the red line indicates the dollar value from investing in the market, while the blue line, which is very close to the horizontal axis, is the dollar amount we get from investing in T-bills. You can see that investing $1 in the market in 1927 is worth a lot more today than investing $1 in T-bills. We've been compensated for bearing the risks of the stock market. So the data we see in reality is consistent with the average investor being risk averse. That's all I want to cover in today's lecture. We wanted to introduce the concept of returns, risk, and risk aversion. We're going to build on these concepts over the next 2 weeks. See you in class.